What's up, everyone? Jason Turley here, back with more pwnable.kr. So, reverse engineering war game, binary exploitation themed war game. In the last episode, we solved FD, in which we learned a little bit about Linux file descriptors, and now we'll be moving on to the next challenge, collision. So, clicking here, we get this pop up. It says, "Daddy told me about cool MD5 hash collision today. I want to do something like that too." And then it gives us the SSH connection line. And if we're not familiar with what this is, MD5, message digest 5, which is a very common hashing algorithm, right? If we echo, I don't know, hello, and we pipe that into MD5 sum, you see we get a hash, a unique random value, essentially, and every single time we pipe hello into this, we're going to get the same exact result. But if we echo something completely different, like please sub, into the same algorithm, MD5, we're going to get a completely different hash. So hash collisions and just hashing in general, it's a computer science term for two inputs, whether or not they're close in value. We can demonstrate that here. So hello. Let me change this, I don't know, exclamation point to a question mark. Even though they only differ in like one character, the exclamation point and the question mark, we get two very different outputs. And if we really wanted to beat this point to death, we could look up hash collisions. All right, Wikipedia, that's a good enough result as any. It says, in computer science, here we go. In computer science, a hash collision or hash clash is when two pieces of data in a hash table share the same hash value. The hash value in this case is derived from a hash function. In our case, message digest 5 was our hash function, which takes data as input and returns a fixed length of bits. So every single time we run this, we're going to get the same length, but totally different values. And they have this neat little diagram here where their values, their keys that they're entering are just their names. And even though John Smith and Lisa Smith are very common, we get two different values, two different hashes, two different areas that these get stored. So hash tables, hash collisions it's a very big and broad, I guess, field of study. You can spend your whole career just coming up with different hashing algorithms, cracking them, so on and so forth. But we're not going to focus on most of that today. Today, we're just going to grab this SSH connection line, go to the server, and then solve this challenge. So slam that in, enter the password. Let's see what we're working with. Okay. So the files of interest are kernel or collision and collision.c, and then with a flag. We don't have access to the flag because we don't have the correct read permissions, but we can read the source code and we can run the binary. So let's run the binary to get started. It wants us to enter some passcode. Passcode length should be 20 bytes. Okay. Python C print A times 20. Wrong passcode. All right, let's look at the source code, see what's going on. So this is a C, C as in the letter C, the C programming language. Let's see, set number. Okay. So on line 3, we have this value called hash code, OX21DD09EC is being defined. We see a function called check password. That sounds pretty interesting. It takes in as an argument a constant character pointer called P. And then the first thing we do is we cast that character pointer into an integer pointer. That's interesting. We declare two variables, I and then result, set both to 0. Okay, so I is the index of this for loop. So we're going to iterate across 5 times, and we're going to do some math, is what it looks like. This plus equals. So we're going to iterate across whatever we enter, and that gets stored in result. And then we return that value. And then what do we do with that value? So we saw these two cases earlier when we did not enter a argument on the command line. It printed out the usage statement. And then when our argument was not at least exactly 20 bytes long, it prints out this error statement and exits. So this is the win condition. This is what we want right here on EC, and then it prints out the flag. Cool. So now that we know kind of what it wants to do, we could look at this in GDB to get a better understanding, or we can kind of just make our own version of this file, I guess, that prints out the values. Haha already exists. Ha ha ha. Okay, so let's copy this challenge binary into our folder. Let's cd into it. Now let's edit it. So let's add some print statements just so this is a little bit easier to understand. So I equals %d, print out the value of I. Let's also print out whatever is in IP. Okay, I think I did that correctly. And then finally, let's print out the result. The result equals %d. Oh, I've been coding in so much Python. I've been saying print. I need to do printf because this is C. The difference is a print with the F at the end is print formatted. So we're passing in these format strings, right? %d. There's also %d for decimal, but there's also %p, I think, for pointer, and L for like a long and whatnot. But Python has print, whereas C has printf or put string. They don't have its own print function. Let's compile this. Turn on strings. Okay. Make that a comma. Recompile. Okay, that's fine. Okay, enter my passcode. So this loop, so I, as we saw earlier, it's being set to 0, and then that increments by 1 all the way up to 4, and then once it hits 5, the program stops, or at least that check function check stops. We see the current values of our array, because we passed in 20 A's. I don't know if that was obvious or not, but we passed in 20 A's, and these are being looked at in chunks of 4 bytes each, because we saw that this is being cast to an integer. I don't know if I have that. See here, it's being cast to an integer, and an integer is 4 bytes. So every time we loop, it's looping across 4 bytes, right? 4 chunks essentially in memory. I should put up like a picture or a diagram of what I'm talking about to make it a little bit easier. Our result never got printed. Oh, I need to put the print statement before we exit the function. Let's recompile it and rerun it. Okay, here's the final result. If we look at that in hex, we get 46464645, which is very different than the OX21DD09EC value that we saw earlier. So how can we get that? Grep hash code .c. Let's do some math in Python. Let's translate this to an integer so it's a little bit easier to work with, an actual whole number and not just hex. And we know it's going to loop across 5 times, right? We see that here, 0, 1, 2, 3, 4. So it's going to loop across 5 times. So can we basically just make this nice and simple and just divide it by 5 and then add that in every time to get our final result once it does all the math? So it looks like here that we get a whole number, but if we add a 0.0 to make this a decimal, we see that 5 is not divisible. We see that this number 568134112 is not divisible by 5 evenly. So we get a remainder. So instead of dividing it by 5 here, let's take the modulus. So there's 4 left over after we do our division. So let's grab this first value, multiply that by 4, and we get this big number. So let's subtract our original value from that remainder. And then as short code in Python, if you want to get the last value, the last return value, you can just do an underscore. Okay, so now we have these two numbers. Let's take the hex of this, as well as the hex of this last one. There we go. So these are our two values that we're working with. This is the one that we want to multiply by 4. If we just take the hex of that and we do this, that won't work out because it wants it to be at least 20 bytes long. So we can repeat this value 4 times. Let's do that. I'm kind of talking out loud, thinking to myself as I solve this. So this is the hex value, but since this is the C programming language, and since we are, I believe this is an Intel, let me go back to my home directory. Yeah, this is a Intel binary, right? It runs on Intel CPUs. It is Little Endian. I believe it says it here somewhere that is Little Endian. Maybe I'm just not seeing it. But yeah, least significant bit. I believe that's what it means. I believe this means Little Endian, and we need to swap the order of these bytes. So Python /x to denote hex notation. And we're just going to walk backwards and enter these values. Multiply that by 4, and then do the same thing for this one right here. Let's actually print this out. Okay, the command line interpreter I'm in cannot understand this. So what we want to do is grab this, we're going to wrap it in these C's with the $sign, and then we're going to add, and then we're going to pass it in as an argument to our program, collision. Smash the enter key. It still doesn't like it. We're doing something incorrect with the length value. It's not 20 bytes in length.
2 hours later.
Oh, I see the error. You guys are probably yelling at the camera. So right here, I have /x to denote, oh my goodness. I have the /x syntax to denote that these are hex values. However, I left that out here. I just have C5, where I want /x C5 to make that the hex value that we saw earlier up above. Now when I smash the enter key, right, it takes these hex values and it translates it to decimal because that's how we have our program set up. And we see the first 4, iterations, the first 4 loops of this program. It has our first input here, and then the last input is this chunk that we added at the end, and then we get the final result of this, which is OX21DD09EC, translated to decimal. And then it even tries to print out the flag. It doesn't work because we're still in our makeshift directory. So if we go back to our home directory, and now we run this again, but it's not called a.out. Here it's called collision. Smash the enter key, and then we get this long flag. So that's how I solved it. I was kind of going crazy there. I didn't understand why it wasn't working, and it was because I left out the /x here. So I did some digging and looking, and OXRick, he makes really good write-ups. Just in general, I know he has a bunch of try hack me stuff. And I was looking how he was doing it in very similar approach, very similar technique, very similar method. And that's when I just double checked and I'm like, oh, I left out that /x to make it hex. and that Python one-liner. So no shame, nothing wrong with looking up write-ups or hints or guides. I mean, heck, that's what you guys do at my channel, right? So there we have it. We can grab this, copy it, and slam it in here. I guess I got logged out because I was taking too long. But there you have it. That's how we solved this challenge. Tune in later, and we're going to keep continuing on in this series. The next one is BOF, which I'm guessing is going to be a buffer overflow, which is a really, I guess, fundamental topic of binary exploitation. You're not going to get very far if you don't learn about buffer overflows. So I'm excited for that. As always, let me know down below how you guys solve this, anything I missed out on, any other ways, tips, or tricks you guys want to impart. So that's it for this challenge. As always, guys, take it easy and see you in the next video.